so you guys had on your tables 3 pieces of paper that's your 3 homework assignments. One homework assignment, instead of a normal physics textbook, this time I gave you guys the cartoon guide to physics.
Yay! Cartoon.
Okay, so it's sort of like a comic book of physics.
This guy looks like Kenny.
Okay, but it still has all the same physics ideas as a regular textbook in it, so I'd like you to read pages 3 through 9. Then there's a piece of paper that says to complete the questions. The questions will tell you what I want you to do with the comic book. Okay, so just read, take a look at both of those and you'll figure out what to do. And then homework number 3 was the one that I canceled on Wednesday. So now it's back in, okay, which is the last packet that was on your table that says speed, velocity, and acceleration, but you only have to do the first 5 questions.
How come we couldn't do that
On Wednesday? Because I was worried that I was giving you assignments that you didn't know how to do.
I saw you laughing. I was like, oh my god,
right.
something like a ghost or something.
Our science experiment is arriving, so we're going to be, you'll see we'll have some skaters today that will be observing and getting some observations, some descriptions about.
Science, physical plus mathematics.
Okay, so here's what I would like you to do. We're going to take, maybe a minute on question of the day. Okay, so I'm going to slide this up. Okay, here's what I'd like you to do. Please draw this Venn diagram, like a double bubble. Acceleration is a physics idea, but it's also a word that we use to describe everyday things like cars. Okay, so I would like you to compare what are you thinking about so far for acceleration in physics versus acceleration like the way that people might talk about it with cars or something like that. So in a Venn diagram, you place things that are different in the outside parts, things that are the same in the inside part. Okay, so take maybe 1 minute to do this by yourself, and then I'm going to have you turn to your neighbor and talk about your Venn diagram. What does it mean?
And then in physics, they use it in
what makes going faster or acceleration different from going faster for speed?
And also say that it's mostly measured with cars in real life. But
how is going faster? How is that different? Is acceleration the same thing as speed, or is it like a different thing?
They can measure like a cheetah's.
What do you mean by power?
Acceleration in everyday language. We use it like it's getting faster. Something is getting faster and faster. And in physics, it's more units per second. And they pretty much mean the same thing.
Yeah, mine's pretty much the same.
What'd you say for how they are?
Okay, what are y'all
Pretty much the same thing.
I said they are both like measured.
So you're thinking they're totally different? That acceleration in physics is totally different from acceleration in everyday?
No, you can use it either way.
So what do you feel like is related about them?
They both use like velocity.
So when your mom talks about her car, she says what velocity it's
My
going?
mom does not know what velocity means.
I don't. My mom doesn't talk to me about her car.
Or like on a car commercial, you're saying that they would say
miles per hour.
So what's that? Miles per hour.
That's your speed.
Okay, so then what's an acceleration? So you're saying that in everyday language about cars, the miles per hour is a speed and an acceleration. Like you're saying it's kind of the same thing in everyday language. Okay, but then what about in physics?
In physics, it's velocity.
So you're saying
change in velocity.
It's the change in velocity. That's
Divided by
acceleration.
the time it took.
Okay, so you're saying in physics, it's the change in velocity divided by the time that it took. But in everyday language, acceleration is just speed.
Yeah, like the miles per hour.
Okay, so it sounds like that you're thinking that there's sort of 2 totally different ways of saying acceleration. That everyday acceleration is like totally different.
Like they seem like
Okay.
they seem like they can be the same, but then I never hear the word velocity. I'm just like this just now trying to say
Right, it's kind of just a physics word.
Everybody's just talking about my car can go like 100,000 miles per hour or something like that.
Yeah, like
Yeah.
Yeah.
Okay. So when other people share their idea, you might be able to add something to the middle of your Venn diagram. Because right now you
But
don't
how
have.
else can acceleration be used in everyday life?
So you're gonna listen really close when other people are talking and see if you can add something. Maybe you just have it already. Okay?
Everyday life and
50 and 30 seconds.
did you have anything for the same?
0 to 50 in 30 seconds.
Like they usually measure it in like miles, and then in physics they measure it in like any kind of units, like feet, kilometers, and inches.
Okay, so you're saying that in everyday life, acceleration is in miles, but in physics, it's in kilometers, feet, inches, like all different kinds of units? Okay, so does anybody have something that they would like to add or change about Samson's idea? Okay, Polina?
Well, what I think about like are we talking about like the difference or like what?
Either way.
Okay, like the difference. I think like the difference is like a lot of people don't say like in everyday language that they don't say well the acceleration is the velocity divided by the period of time, and so I think they more take it as in like miles and just speed and not like okay it's velocity. So I don't think they take it as velocity. They just take it speed and miles.
Okay. So you're saying that the difference is in physics, you use the word velocity and you would talk about the change in velocity over a period of time, but in everyday language, people would just talk about speed. They wouldn't really talk about velocity. Okay. Okay, I'm going to take one more idea and then we're going to go out in the hall. Okay, Liliana, what's your idea?
Adding to Helena's, like, when it's science, they like use more specific words, like more, like special words that are like, you don't say it like normally. You just don't say it a lot unless you're like doing science, cause yeah, and like they usually just say miles per hour. When
In regular, like
Yeah.
just talking about regular things?
when you're talking normally, so they don't use like that big of words.
Okay. Okay, so it's like you're saying that there's special words just for talking about physics compared to everyday stuff.
Well, they use it mostly for you.
Okay. All right. So keep your orange paper out on your table. We're going to keep coming back to this today. I think by the end of today, you're going to have way more ideas about what acceleration is. Okay, all you need is something to write. Wait, sit down. Okay, so I'm going to give you guys a paper, and I would like you to put your name at the top. The person that you've just been talking to is your group for this activity. Okay, what we're getting ready to go do is we're going to watch some people rollerblading in the hall. Miss Stein is one of them. Mr. Little is our other rollerblader.
Mr. Little!
So, it should be fun. Okay, here's what I want you to pay attention to. Okay, what I want you to pay attention to about our rollerbladers is you've started to get some ideas about speed and velocity and acceleration. I'm not going to have you measure anything, I just want you to use your eyes and look at them skating. But here's what I want you to pay attention to and take notes about. How do they get started when they're, you don't have to write them down, these are all on the sheet. Okay. So just listen for right now. So how do they get started? Like when you're standing there on your skates, how do you get yourself moving? How do they speed up a little bit? How do they just coast? You know, like, how do they just stand there and roll for a while? And then how do they stop without running into a wall? Hopefully.
I might be doing a lot of that today.
So like, how do our skaters get moving? How do they stay moving? And then how do they slow themselves down enough to be able to stop without crashing?
Damn, these guys. No, wait, where are you going? You going? Wait. We're not ready yet. Oh, yeah.
I was like,
Watching the feet. Pay attention to the feet.
I know, like this hockey Mr. Little.
It's like the way he stops, it's like makes the T.
I know, it's like
Whoa, like it stops, like when he stops, like this, one of his, like four of his wheels on one leg just like stops
Makes a T like this.
Yeah, just like pulls it to make it stop, and then the other one is right.
When he drags his foot, he loses momentum, and he loses speed.
Yeah, which makes him go to a stop.
exactly. Down here, like around here, stuff. Okay, I'll just take that
Like that.
Speed like that? That's kind of cool.
I knew that when I did go skiing. I
go like this. I
do that when I go
do the T thing.
Alright, so can I hear some of your ideas?
Well, when he stops, he makes a T and he grabs his skate.
Like this?
Yeah, like this. So he loses momentum and
Why does he make a T?
Because the T has to drag it drags along the ground.
when it drags,
Come here, bro.
Make a path, guys.
when he
Drags
does
along the
that,
back and it acts like brakes.
It acts like brakes. Can you say more about acting like brakes? Like, what does that mean?
Like the wheels kind of drag on the ground because it's going.
Okay, so I heard dragging and that the wheels aren't rolling anymore. And then I heard something about momentum. Clayton, can you tell me your momentum idea? Or whoever's idea it was? Samson's idea. Tell me about momentum. What do you mean by momentum? I don't know that word.
That's fast.
he loses like more power.
So he loses more power, like more, when you say power, do you mean like just how strong he's going forward? Okay.
And then which makes him lose speed.
Okay. Okay. So how does he, what are your ideas, all of you guys, what are your ideas about how he gets himself started?
I think he pushes onto one leg. Pushes from one leg onto the other.
Like pushes his
Like if he's still, he push and glide just like.
So how, if he's just standing there like this, how does he push himself?
He does like the
Puts all
same.
his weight on one leg and then jumps off. And then
Oh, so you're noticing like this like side to side movement that he does?
And like he does the same thing, but like instead of a T like really close, he just like pushes off.
Oh, so you notice that he made a T and pushed on the back?
Pushed on the back.
So
and then
why can he push on the back foot?
Because
why does that
that's
work?
not rolling, and like it's like stop. So
Okay.
the wheels don't spin that way, so they can't roll.
it only spins when it's
Okay. What if the hallway was made out of ice?
out of ice. It will start slippery.
So like, could he do this?
No,
Why?
because then like the ice is too like slippery, so like it would just go.
So like even his back, even the T wouldn't work because you're saying it's too slippery.
I think he would have to just fall down.
And it's rubber.
Okay. Okay. So you guys talked about that he makes a T close together to stop and a T kind of far apart to get started. Can you tell me more about the T close together to stop? Like, why does that work?
Oh.
So he's like skating, and then he makes this T. Why does that work?
Cause like it's like like I said the wheels aren't rolling because like
On the back foot.
on the back foot, but this one's still rolling.
Okay.
This one's like gliding, but like also like on like not moving.
Okay.
It's just like what's it called?
I don't know what that is.
Like scraping or dragging.
Yeah, dragging. Yeah, and like when he starts, like
With this is like when you're
Yeah,
talking about the T but spread apart.
yeah, like he has no like speed over there. Okay, so like when he brakes, he has speed, but like he starts dragging. But when he like starting, he doesn't have no speed, so he pushes off. That's why it doesn't like drag.
Okay. Okay, and you're saying like we talked earlier that if he was on ice, it wouldn't work.
It would.
Can you tell more about why it wouldn't work? Would the close-up T for stopping, would that work on ice?
I don't think so either, because
Okay, why?
like even
like pretty much on ice, the wheels won't like roll at all. Well, they like really like they'll just like spin once every like I don't know maybe 3 seconds.
Okay.
Because like on ground it's solid and everything, and like they actually be touching the ground every time. But on the ice, and on the ice it doesn't like it like it just like slides on it.
Why? Bradley said something about sticks.
Yeah, like it actually sticks to the floor, but on ice it like it's really slippery, so the wheels wouldn't have like any grip and it wouldn't be able to move. Okay. And so if you tried to move on it, you'd end up going like this.
Yeah, you just fall over.
Like that or something.
So I'm hearing you say, Bradley, that like not only would the dragging not work on ice, you're saying that the wheels wouldn't even roll because they wouldn't grip.
They don't have grip on it. Like they don't have metal or like little tiny.
So like they would have to have like teeth or something in order to work
or
on
like
ice.
it would have to be a metal line, like
cars,
like a skate, like an ice skate.
Yeah.
Okay, all right, I understand you. Okay, so get all of these ideas down on your notes. What's going on with her skates and with Mr. Little's skates?
It's a surface.
And make notes. So you might want to get down there and check out what he does with his feet.
That was practice.
Oh, so what are you guys thinking?
Well,
How do they get themselves started?
Move their feet out so like they can get some speed, and then like once they're like going, they just kind of like stop and let it roll.
Okay, so
And then they end up kind of slowing down a little bit. I think it's a surface because if it was a bumpy surface, it'd be harder for them to go like smooth and as fast as they are.
okay, so Shauna, you noticed that he moves his feet out. How does that work? Why does that make him go?
Because like the wheels, and then like because of the flat surface, it just like goes and it makes them move.
Okay, what do you think the like side to side movement is doing?
It makes them like get out of the straight path so that they can go faster, and then they get back into the path.
Why does it make him go faster though?
Because he's pushing.
Oh.
But like when I think of like, you know how like she's moving?
Yeah.
Like you know how she goes out?
Yeah.
And then like she kind of goes in. It seems like she's like pushing like air back.
Oh.
Like because when she goes in, like it pushes the air back so she can move through.
Okay. So you're saying that she's part of how she's moving herself has to do with pushing the air out of the way?
Yeah.
Okay. What if the floor was made out of ice?
Ooh. Ice and roller skates or ice and an ice skate?
Ice and roller skates. That's a good question.
Then
It wouldn't work as.
I mean, there's still air.
If she was like,
it
if she
wouldn't
was
work
just
as good because like it's just kind of flow where it's like.
yeah, like how we're doing the carpet, it's hard to move like when you have
because,
like
like,
a
tension's
really
getting caught.
rough surface, like yeah, you get like the tension, but then like now she's only rolling on like a flat surface, like on the table. It's smoother and like easier to move.
So then, would ice be even easier to rollerblade on?
It'll be harder.
no, but
Why?
like
Because they'd
it's
have
like-
like little cracks.
Yeah.
Little crack. Wait, tell me more about the cracks.
Like, cause like cracks, you can like get caught more easily there.
In the ice?
No, like not in the
no,
ice,
because
like,
they
but,
have
like,
those machines that smooth out the ice.
okay, so like the ice is smooth out, but it's not technically like I feel like the wood it's gonna be better.
But if you're doing it on those, but like there's like certain things that are made to go on ice. Those aren't made to go on ice.
Why not? Why wouldn't they work?
Because they're roller blades.
Yeah, but why?
They're blades, like they're.
Oh God! Put your physics brain in. Why wouldn't they work?
That's wheels and like if you have a roller blade or like I don't know what's called roller blade, ice blade.
Ice skates?
Ice skates, yeah, ice skates. Like do you have that sharp thing like to get through the like the ice and get yourself moving, and then use like the ground to get yourself moving. But then like if you're using the ice, it could be like even more slippery, and there's like not like you can't get that like tension and stuff.
Oh, so
you
like
can
no
stay.
tension with the ice?
Yeah.
So like how she's
wheels.
pushing a
Those are
little
just-
bit,
yeah.
you're saying that there would be no tension on
But
the
that
ice?
blade is like made like so you
For
can
the
like
wood.
for the ice.
Oh, for the ice,
Not the
yeah.
ice.
The blade, yeah, for those kind of wheel. But then, like, if we have these kind of wheels, I don't think it would work as well on the ice because the ice isn't, because like what Disney said, they have like necessarily like shoes for ice skating.
Yeah.
So like here they have shoes for like roller skating, and so like you can see on the wheels there's like little like spikes and like to show that it's been on the floor and it has tension and it can go faster. But it's on the ice, it can't have any tension because it's ice and blades.
Ice.
So
Ice and wheels.
wheels.
But Miss Bratton,
It's like a car. Like if there's ice, you might like slip and like go out of control.
Miss Bratton, but like you know how like if you were to buy, I'm gonna skip Helena's example, but like if you were to buy a new pair of skates where they had more smoother wheels,
Of these kind of skates is what you're talking about?
yeah, rollerblades or something, would, if you're going like really fast and you try to stop, would you keep going because the ice can be slippery at times?
Yeah. Like when
So
I
wait,
think of it,
or
I think
like
of-
Tell me
like-
your whole story. You're asking if you had brand new rollerblades on ice.
Yeah.
Okay, I'm with you so far. So if you had brand new rollerblades on ice, you're asking when you stop, would it be slipperier?
Like, if you were to like go really fast down the ice, and if you were to try to stop, would you start sliding because on like a surface like this where it's smoother, but the ice is the rollerblades aren't made for the ice?
Okay. So can I ask you a question back?
Yeah.
If you have rollerblades on ice, how are you gonna get started moving?
to use like
Could
force
you like
movement.
push yourself?
Like, yeah.
Tell me more
yourself.
about pushing yourself. Would it be
Push
like on
yourself
here?
off.
No, it wouldn't be the same.
Are you done with this question?
But
Okay,
I
wait,
think,
wait, Sydney, what were you about to say?
I was gonna say like, could you like push yourself off of a wall or something?
Push yourself, like, so you're saying like you might be able to stand on the ice and reach back and like push off of a wall behind you?
Yeah, you could do that, or you could.
Why, what about, could she get started just the same way that she did on the floor here?
I don't think so.
Why?
Because it's wood compared to ice. And
But why?
Because it's not the same tension going on.
Helena.
Okay, tell me more about the tension.
The tension, okay, I feel like it's not going to be the same because like here it's more like flat and more, what is it called, wood, so that it's hard. And so like she can go smoothly and the tension will go like that. But then when it's on the ice, it's not as like, well, it's not like hard. I'm not sure what I'm trying to get to.
oh, well,
I'm not sure what
I-
you're
I-
trying to get to,
I-
Nina, that's why I keep asking you questions.
What I was
No, also, the way I think about it, like if like you rode rollerblades on ice, like, when I think of it, it's kind of like a car. Like when you like rolling on ice, you might go out of control, and it's like really too slippery because like the blades, they're made for a flat like surface like this. But like if you're using rollerblades, they roll like automatically, basically, kind of like you could just like stand on a hill and like, I mean, they're gonna roll because they're rollerblades, but like
What about on ice though? Would they roll?
you could like you can get them going, but like I don't
Well,
think
how?
they wouldn't go.
Why?
Because like maybe one could be that the rollerblades aren't made for ice.
But why? Why wouldn't they work? Be a rebel. I want to use my rollerblades on ice.
Because they're not. I don't know how can I put this.
Like, what does it take
Like,
in order to
for
get the
example-
rollers rollering?
For
Like,
example,
how do you get them
Like
rolling?
energy, like you have to use like energy to like
And to push
move yourself. You have to use like force, like to get
Okay.
yourself going.
Okay, so tell me about the force that she was using to get herself going on this floor.
like Miss Bratton, can
Yeah.
I use an example from
Sure.
like real life?
Of course.
Okay, so like from the wheel incident where you said, where I was talking about how I think that rollerblades aren't made for the ice,
Yeah.
I would use the example of like a car, and I think that like when you're speeding and you try to use your brakes, sometimes you can slide because your wheels stop and they lock up, but the ice is like really slippery because it's water, and you just slide on it until you get to a stop somehow. But
I don't think.
Like,
What if you tried, what if
Well,
you're
I think-
stopped on the ice and you try to go really fast? What do you think would happen?
if you
I don't
stepped
think
in
you
the
can go
ice,
really fast.
Why?
on road.
Like, why can't you get started going really fast on ice?
Because like the ice is more like of a thicker kind of. Like,
Okay.
I think like it's more like a thicker, you know, because like it's all the water like frozen, and so I think it's gonna take more effort to start going faster, especially because you know you're using the opposite of what you're supposed to be using, and so like if you're using a rollerblade on ice, then in like of course they're gonna go, but they're not gonna go as fast enough because it's gonna be harder to like get through like ice.
Okay.
I have a perfect thing.
Okay, so write it down.
But Miss Bratton,
Yeah.
also I think that rollerblades aren't made for ice because isn't the point why they have ice skates is because of the blade?
Well, yeah, but I want to know why. Like, why did they invent them to be different on the road than on the ice? Thanks. All right, so we just saw two skaters out in the hallway doing a couple of different laps up and down the hall. And the things that I asked you to pay attention to was how do they get started? How do they like keep themselves going? And at the end, how do they make themselves slow down and stop without running into a wall? Okay, and I heard some totally different ideas at each end of the hallway, so I want to have you share out your ideas so you can combine them together. Okay? So, Juan, you had your hand up just now.
Can I go get some water?
Yes.
Mm-hmm.
Clayton.
I thought they do like a kind of like when they're about to go, they do like a push. We have to run in at school. I saw Mr. Lord doing like a, you know how they went sideward?
Yeah.
That was, I think it was kind of like he was pushing, and then like he would glide for a couple minutes.
Okay.
And then he would push again, and then glide, and then to build, and then when he pushed and went sideward, he did the sideward thing. He built momentum to go faster.
Okay.
And then when he was standing still and gliding, that means his wheels wasn't slowed down all the way. It still had a little bit of speed. That was still making him go.
Okay. Can you tell more about like what's actually pushing? How does he get himself started?
About like the force in his foot
Okay. The force in his foot.
or his calf.
Okay. And then what's he pushing on?
Force. I mean, no, the skate.
So Mr. Little's foot is muscles are pushing on the skate. And then what?
And then accelerates.
But,
Skate.
so what's this? Go ahead.
Skate on the floor.
And so then you're saying that this, so Mr. Little pushes the skate pushes on the floor, and then why does he roll? Like, why does he get going?
Because
Can you tell me the whole story?
because like when he pushes off, like he's not rolling and he doesn't have no speed, so like he doesn't have to stop and then go.
Okay.
So like he just pushes off with the like the rubber sticks to the floor,
Okay.
so like it doesn't like slip like on ice. But
Okay.
like on this kind of floor, it just like pushes off.
Because it sticks to the
Yeah.
floor?
And then like when he like instead of like this is going forward.
Yeah.
Instead of going like this, he pushes off like this, but then when he's going forward, he's going like this.
Side to side?
Yeah.
With his feet? That's what Clayton was
It's like-
talking about, the side to side?
Yeah, because like the side to side is like it's like pushing off, but it's also it lets the wheels roll
Oh, so it's both pushing and rolling.
once it's already like.
Once he's got some
Yeah.
movement going? Okay.
Well, actually, in the sign, after got some movement going, she would like she would move the air like this, she would move the air out and then in, out
With
and
her,
then in.
she was doing her feet like this,
Yeah,
right?
like that. And so then it made it so that she would be steady and she can control it. And then it made her like with the wheels would. Well, she's just pushing the air out and then pushing it in. So then, like gravity, all about it. So then.
Wait, tell me more about the gravity part.
Well,
I don't know what you mean by that.
like when I said like she's pushing it in, and then she push like she has the air that she pushes it out,
Yeah.
so that it goes like so it's making her go faster and faster.
So you're saying that when she pushes her feet towards, like she slants them and pushes towards the middle and then she pushes them out again, that it's like grabbing the air?
Yeah, like it's like pushing the air out and then pushing it back in and then making her.
Okay, and then what, I don't understand what that has to do with gravity.
Well,
or maybe, or are you changing your mind that you don't mean
kind
gravity?
no, not really gravity, but like it has like a lot to do with like motion of the air.
Okay, motion of the air. Okay, Jaden.
I think that when her feet are coming back together like this, she's kind of pushing the ground, that's right here. She's pushing it back and it shoves her forwards, which is like in the jet engines where it has the, like if a frog jumps off of the little thing,
lily pad,
then it shoves the frog forwards and the lily pad goes back.
Oh.
And when she's going like this, it's pushing her forwards and making the ground go back.
Okay, so you're saying that it has more to do with her skates touching the ground than with her body touching the air.
Yes.
So, Helena, do you hear how his idea is a little different from what you're saying about that she's pushing the air in and out? He's saying that maybe she's not, maybe it's not so much about the air, maybe it's that she's pushing the floor. Okay, so you don't have to decide right now, but I want you to hear that those are kind of two different ideas about why the side-to-side motion of the skates might make her move. Okay, Liliana.
Well, since the surface is flat, and it's like hard.
Yeah.
Like it would make well, it makes the roller skaters go like more at a constant speed.
Okay.
But except for when they like start building more force, so they go faster. That would be like a little bit more than when they're just rolling. But if it was a bumpy surface, it wouldn't be so constant. It wouldn't be so like alike with other times or others. Because like they would go slower and then faster, and yeah.
Okay, so I heard a couple of really important ideas in what you just said. The first part was that you said once they're rolling, they could move at a constant speed, but when they're applying force, you said maybe that it was a little bit more. So when you're imagining, can you imagine like if we graphed their speed, what would the graphs be like? Like what would the constant speed be like versus the part that you were saying where they apply a force and they're getting a little more?
Well, it would be like for a few seconds, it would be like a straight line.
Which kind of straight flat or straight diagonal?
Straight diagonal.
Okay.
And then it would be like a steeper, like a little steeper line.
Okay.
And then it would.
When would it be steeper?
Like after a few seconds.
Why?
When she pushes for more speed, because it makes her go faster.
Okay.
And then it would be like another normal line.
Like by normal line, do you mean diagonal?
Yeah.
Okay.
And then it would go steep again.
Every time that she adds a force,
Yeah.
you're saying it would like go steep a little bit?
Yeah.
Okay, and then what about when she is coasting and then stopping herself? What do you think?
It would like get more sideways every time,
Like it would go by more sideways, you mean like this?
Yeah.
Until when
she stops, like a solid stop, like she
solid. This is being solid stop.
Yeah, like she just stands there.
Okay. Okay. Jael gets the last word, and then we're moving on. Go ahead.
So I kind of agree with Jaden, but like instead of like him saying like going inward, like I think it's going outward.
Oh. So wait, tell me more about this.
Okay, so like you know how Jaden said like when the frog pushes off this way, like the leaf goes that way. I agree with everything, but except like not going in like the skates, because like when the skates are going this way, they're just like what's it called? Coasting.
Yes.
And like when like they're going this way, they're like pushing off.
Oh, so you think that the pushing force happens every time that the skater turns their feet out? and
Well,
pushes?
like, it's like,
You can show.
okay, so like it's like this.
Uh-huh.
This one glides and this one pushes, and then this one glides and this one pushes.
Oh, okay. So you're saying that it was like that the skater had a gliding foot and a pushing foot,
Yeah, but they switch off.
and that the pushing foot is the one that's pushed to the outside. Okay, and then, but then like Miss Stein was doing this thing where she was moving her feet in and out and in and out.
Oh, okay. So, yeah. Well, okay. So maybe there's like two different kinds because like for Miss Stein, the one that's going out is like the gliding one, and then the one that's going in, it is like pushing backwards, like Jaden said.
Okay, but then you're saying like when Mr. Little would push with one foot and push with the other foot, but he would glide on the opposite foot. Okay. So you're saying maybe we have to have two different kinds of ways of talking about skating depending on how they're skating. Okay. All right, so here's what I would like you guys to do next. I'm going to come around and talk to each table. So you can add any ideas that you want to the front. You can always go back to the front page if you want. It asks you to represent the motion. Okay, and both Jael and Liliana have already started doing this in their words. Okay, Jael started to talk a little bit about something that you could put in the top part of your representation. Here I want you to sort of draw a diagram of what you saw happening with your skaters. So it could be maybe like that you draw a diagram of the hallway and you write about like this is where he was speeding up, this is where he was coasting, this is where he was slowing down. Or it could be like a detailed sort of diagram of like how Jael was starting to talk about the gliding foot and pushing foot. You could draw something like that. Okay, and then the bottom is the part that Liliana was already talking about. That if you had a position versus time graph, like we've been working on with speeds, how would you indicate the changes in the person's speed? By drawing diagonal lines and steeper lines and flat lines. Okay, so you can work with your tables about these two different representations. You go from speeding up to stopped. Like what's the, if you don't really have room, so maybe you'll have to draw an arrow and draw it over here. Like what's the picture that's in between here, between speeding up and stopped?
I can't really draw it, but it looks kind of like this.
So you're saying that getting started and then getting stopped is actually kind of the same.
Yeah, you kind of, if you have brake, like the types that have a brake on the toe, right here, then you just drag your toe on the floor and then it'll stop.
Okay, so but here, is he dragging his foot to get started?
But actually, it's like he's moving side to side.
Is that for us?
Yeah, but like he never faced.
So he's moving side to side. That doesn't sound like the same thing as how he got stopped.
When he's starting, he's moving off from a foot that is sideways, and then putting all his weight onto this, and then jumping onto the other foot.
So it's like he has one foot sideways like this and one foot facing forward. And you're saying like it's like he pushes off with that foot and then jumps onto this gliding foot?
Because this one can't roll, so it gets good and it doesn't slide. But this one is still going a little bit, but then he presses down, pushes off, and jumps onto this one, and then he does it with the other foot, and then the other foot.
Okay, so can you guys add to your diagram like maybe a label about how you were pointing here and you were talking about the toe that pushes? Can you draw, like add a diagram, and then Jaden on yours, could you maybe draw a little something about what you just said with the T? Just add it to your diagram. I mean, I see you have the T stop, but like add some details underneath there about the pushing.
Starts pushing off, and then like right in the middle, I think like he's pretty steady, like he's going at the same pace, and then when he gets like closer to the end, he starts slowing down, and then like right here, like right before he starts stopping, he does the T-shape, which then he loses momentum.
Why does the T-shape make him lose momentum?
Because before when both feet were like parallel, all the wheels couldn't move. but then since half of the wheels stop moving, then it would go like half the speed and it would stop slowing down.
So the more, you're saying the more wheels you have, the more speed you have, but then when he turns this one sideways, he has fewer wheels. So like, could he keep this foot off the ground and it would still work? Like, would he still stop if he took that foot off the ground?
He wouldn't stop, but he would go like a little bit slower.
Slower? Okay. So then why is it, when he puts that foot on the ground, why is it that it makes him stop?
Well, since there's like a lot of weight in the background, like perhaps like I'm carrying like a really heavy backpack, that would make me slower, and if I had no backpack, I could run faster.
Why?
Because there's less like weight, and I have more like free and stuff. And so if you drag your foot, it's like the same thing.
So you're saying that dragging is what makes him stop, and if he had a heavy backpack, would he drag even more? Like if you're pushed down because you have a heavy backpack, that would make you drag even more? I get it now.
That's fine. Like they push up, like they go like that and they go like that. They don't exactly just go. So they actually move their feet, so they can get faster and faster, and then they do what this time.
Okay, so now that you just did all of that, now I want to ask you again about the ice. So why can't you rollerblade on ice?
Oh my gosh. Because you won't be able to do the same thing.
Why?
Because it's not the same like thing as a wood and an ice floor.
Okay, why? What's different about that?
That's why. I'm like, you gotta be specific. You're not just gonna go on forever. It's like, why? Why? You be like, because the candy is not orange. Why? Because I can dye it orange.
Okay, I'm serious. Why can't you rollerblade on ice?
I know.
Do you know the answer, Miss Barton?
Yes, she does. She does.
Can you give us a hint?
You have your own hints.
Well, like kind of comparing, like with my foot, I can go like that. But like if I have socks on, I can go faster.
Why?
Because there's more tension going on. Don't ask about the tension. Wait, isn't it because you can't maybe because like you can't like gain speed and keep it at a constant speed.
Okay, I like this idea. Tell me more about it.
Because like you don't even know. Like when you're rollerblading, like you know how like she's saying that you're like gaining your speed, and then you're able to keep that constant speed. But then like if you're on ice. And you have rollerblades, then you can't really like you can gain a little speed, but you can't like it's kind of hard to keep that speed going because you're on a different kind of surface. So like there might be at a point like when you run across something that it'll be like it might stop you or something. You might get caught in something because like your tensions are like it's versus each other, so it's not made for each other. And then so like you'll be able to get going, but then there might be something like that'll stop you and slow you down. Then you have to like get your speed going again, and then like it might be a little bit harder like to stop this time because it's slippery, and so like you have to put more force into it, and like versus just like here you can just kind of stop kind of easy, but then like there you have to like really put more force and like move like energy and your body into it. But then is it mostly because of us or the like rolling the wheels? Is it us or the?
Is what us?
Like is the energy that we use? It's the wheels, because it's the wheels. Because doesn't it matter what the wheels are? Like compared to like wood wheels and then like
does it matter that rollerblades have rubber kind of wheels? Yeah, I think it matters.
It matters because so it won't only matter that we're just pushing harder and harder and harder to get us.
It matters what the surface is made out of.
Yeah, what the surface is made out of. So that's why you can't exactly.
So, but my question is, why does it matter? But I'm not going to stay here and ask you because I can tell you're getting tired of the why questions.
Can you just why?
You guys are drawing.
In ice question.
Yeah.
Well, I think you can't do it like in the wood because like if you keep going, the surface will get hotter. So it since like you keep going on it like sometimes even faster, it might start melting and it won't be the same. Then it'll turn into water, and so like you won't be
You
able
must
to.
be skating really fast to melt a whole ice rink.
Oh my god.
Not the whole thing, just maybe like a little part.
Oh,
Like-
like maybe just a little bit under your skates.
And that
Yeah.
will affect it a lot.
Like you go and like it's not gonna be cold that much once you roll on it
Well, no, it won't.
Why?
Because if it's melted.
because you're like there's 4 wheels, so like the first one makes it doesn't make a big change, but then the second wheel passes by and it'll make a little change, and then after the 4th wheel it'll make it like a little bit warm, but not that much. But then once you roll on it again or you turn around or something, it'll get warmer and warmer until there's a point where it melts.
I don't know. I've never tried to rollerblade on ice, so I don't know if it melts. But maybe.
Or there might be the weight that the ice isn't so, it's pretty fragile, so maybe there might be some cracks and you roll on the crack and maybe it breaks.
Yeah. What are you drawing, Shauna?
I'm just like drawing some of the movements, like speeding up, changing direction, and coasting. And like I use like what I heard from the classroom, and for example,
So you liked Giles' gliding foot,
Yeah.
pushing foot?
because
What do the arrows mean?
well, that's like the direction that they're going on.
Oh.
This foot goes out, and this one just kind of glides
Oh, I
and goes
see.
forward. And like for changing direction, like the body turns around, so there's like the arrows that are kind of like going around.
Okay. Okay. And then tell me about this graph.
Well, like well, you start off, you have to kind of like get a little faster so you actually go somewhere, and then you start slowing down a little bit, so you have to pick up your speed.
Oh, so you're saying like at this point, this is where you have to push.
Yeah, and
To
which
gain
is like
speed.
using this model.
Okay.
And then you just go at kind of like a constant speed because like you've already went fast, so you're still like you still have a lot of speed. So and then you just kind of roll, and then your speed decreases, and then you get to the point where you
This is where
eventually
you
slow
stop?
down and stop.
Okay, I want to ask you about this one. Your label says that this is decreasing speed. What is this is position, right? Along the side. So what does this downward hill really mean? Go
When
ahead.
it's going backwards.
So Liliana says this doesn't mean decreasing. This means going backwards.
Well, if it was to decrease, it would be like above, like like this.
So like
maybe it
not
would-
quite flat.
Yeah, like a little higher than flat.
So we do this thing over here, but just instead of drawing it, we do a graph.
So do you agree
Yeah.
that the line you have means going backwards?
Yeah.
So how would you, you don't have to erase stuff, just maybe cross the segment out. How would you show decreasing the speed?
Like what Liliana said, it wouldn't be exactly like a flat line, but like a little bit higher.
A little bit higher than
just
flat?
Eventually.
Okay, what does this little bit right there mean?
That's where like the slowing down changes to the stop.
Okay, but what does the going down mean? So, did you ever see them skate backwards?
No.
Okay,
So I have to little skate go flat.
there you go. That's the good line. Yep, so this means, now when I look at this means constant speed and then getting faster and faster, and then like kind of constant slower speed, decreasing until totally stopped. Okay, I get it now.
Oh man.
Okay, good. Yes.
But this is a little weird right here. How I use it like arrows to describe.
I understand that. That's like how she... Okay. You have a lot of diagrams. Tell me what's going on in your diagrams.
Mine or hers?
Either one. What's going on, Amy?
This is, I drew both of them. Miss Stein.
Okay, because they have different kind of skating. Okay.
Ms. Doolittle started off as the same as Miss Stein, and then they sped up like kind of different, and then they're still speeding up right here.
Direction.
And then they were coasting the same, and I'm drawing them slow down. They slow down different.
Okay. So, Jill, tell me about your graph, because you already sort of talked to me about your representation, but tell me about your graph.
Okay, so I haven't labeled it yet and everything, but like right here, he's speeding up, like I kind of did the same thing, but instead of drawing past it, so like from here to here is like.
So you're saying, this is neat, so you're saying that this part of this picture goes with this part of this graph? Okay, cool.
And then like this part right here is the coasting part, but like since like he already got enough velocity, he's going a little bit faster, even though he's still going like this.
How do you know that this is faster than this?
Because like, right?
No, I mean on your graph. Like, how do you know by looking at those two line segments that one is faster than the other?
Because like on the blue paper we had the other day, it said that the steeper it is, the faster it's moving away from you, and then you move.
Yeah.
The like more flat it is, it's slowing down, coming towards you.
Yeah.
Not coming towards you, but
towards you would be like if it was angled down.
Yeah.
So then tell me the story of what's happening here.
Here it's like it was going fast, but then it started slowing down because like it's more in a flat line, and then but like if I drew something like I had to draw something a little bit diagonal, because if I just do it like straight, it would like mean it stopped like this, and it didn't because like it slowed down, then it turned.
Oh, and then he turned around. Gotcha. Okay.
I got a question.
Okay. You have a question? Okay, go for it.
How do you you can't draw when it's changing directions, right? Or
well, you can because this is position. So how would you show that he was going fast, but going like from 10 meters to 9 meters to 8 meters to 7 meters? Yeah, but still forward in time, right? Yeah. Can't go back in time. Yep.
It's kind of like, is this like, I forgot the question. It's like, so, like when you're coasting, are they going constant speed the whole time? And then when like they're speeding and changing directions? And I asked you my question was.
So you're asking when they're coasting, are they going a constant speed?
Yeah.
What do you think? What did you see when Mr. Little would just kind of roll? What do you think?
At first I said yes, but then I said no because he's not like applying any more force or nothing. So he's gonna start to slow down, even though he's not braking a little, and then he just stopped.
Okay. So you're saying, it sounds like you're saying that what you saw him do, it seems like maybe at first he's going at a constant speed, but then because he doesn't add any more force, he slows down a little bit. Okay, so like, what if this could go forever? You know, what if this paper could go forever and he just kept coasting? Can you keep coasting forever? Why not?
Because he would slow down and just stop.
So eventually he would stop if he just kept coasting forever? Okay, so I like the way that you drew this line, and here's why. So this part of the coasting looks like that he's still moving forward. But then this part of the line, he's not moving forward anymore. But I like it because that is sort of how it looks, right? Like that he's rolling forward, and then he stops for a little bit. Does that go with what you saw him do?
No.
Did he stop before changing directions?
Yeah. Because like when they was taking turns, like he'd go and then he'd just stop. And then you turn around and then go again?
Right, and so I like how you drew this change in direction this way because it's still going forward in time, right? It's going forward in time, but it's going backward in position.
Yeah.
I like your graph. I think it makes sense. I think it looks good. That's okay. Does this go with what you saw?
To me, yeah.
Yeah. I like it. I think it looks good. Yes, of course. Juan, what did you draw, and do you have any questions?
Oh wait, which one?
Whichever one you want to tell me about.
I did this one because he started out fast, but then he started slowing down when he was going to change direction, and then he didn't move.
He had to stop for a little bit.
Yeah, he had to stop. And then he started to move back fast.
Okay. Yeah, I like that one. How does he make himself make these changes? Like up here in this picture, how does he make himself go fast or make himself not move?
All right, so it looks like most people definitely have a drawing of what they saw happening for the top diagram, and then I think most people also have the graph at the bottom. Looks like a couple people maybe still need a couple of minutes to work on your graph. I'd like to put a couple up here on the projector really quick before we still have about 4 minutes left of class. So I want to feature a couple of people's diagrams and have you look at them and see if it gives you any additional ideas. Okay, so Clayton, can I have your graph?
I want my little series.
You can sit right there.
Hey! No.
All right. So Clayton, can you use your pencil or your finger? Can you talk us through what your graph means?
Well, I kind of did Mr. Little, and when he first started, he speeded a lot, and it basically to 4 meters or to the 4th position. And then he starts coasting, which is he's coasting and it's still kind of speeding, but then he stops because the coasting, since he's not forcing nothing or applying more pressure to it, it just stops, and then he just is stopping for a couple seconds. And then when he changes direction, that's the reason why I stopped, because he changes direction. And when he changes direction, it goes back. It's basically still speeding, but still going down in time.
Okay. Can you tell everybody a little, you had an interesting idea about coasting. Like when he's coasting, you were describing your theory about not adding any more force. Can you tell everybody about your idea of coasting?
You can't coast forever because since you're not, when Mr. Little was doing the sliding thing, he was applying pressure, but when you're coasting and you don't have no more force, so it just at first when you have a lot of speed, it just coasts for a minute and it's still going really fast at first, but since you're not applying no more pressure, it's going to stop sooner or later and just end up not moving.
Okay.
Because you can't coast forever.
Okay. Do you have any ideas why you can't coast forever? What's making you stop?
Oh, well, the wheels, they when they're speeding at first, the wheels, how fast they're spinning, and if you don't have, then eventually the wheels stop speeding because they just, I guess your weight's kind of going in on it, and then basically is a brake, and it makes it stop.
Okay. So this picture of your graph is that he's coasting, but he's getting slower until eventually he's not moving. Okay. Does anybody have questions for Clayton about his graph? Do you have a question for Clayton?
I did my goal.
You did yours wrong.
Yeah, because this makes sense. Because mine is going speeding this. Mine is going speeding up, and then the coasting part, I said, it still had the same velocity, but I wasn't thinking of the
Oh, you weren't thinking about how with the coasting you're actually maybe getting slower? Okay, Liliana.
The line sideways where it's not moving anymore, it always reminds me of those things they have in the hospitals when the heart stops.
Yeah.
Yeah.
And it makes that buzz and it makes a flat line. All right. I know we still have one more page to go on this. Actually, 2 more pages to go on this packet. But you don't have to. If you want to work ahead, you can, but you don't have to.